Good day all. I'm Mr. Madubid, also known as Professor Quantum. I'm a medical physicist at University College Hospital Ibadan, but I am fully involved with physics education, especially for secondary school students. And I've been in this business for a very long time. I actually taught in so many secondary schools before I'm switching over as a medical physicist in the University College Hospital Ibadan. As a matter of fact, I have a master's in medical physics from the University of Lagos. So let's go. I want to present to you a concise physics preparation for our WAEC, which is coming up, as we all know, August the 27th. It's going to be a wonderful experience because I seek to bring physics from the level of abstraction to which it has been erroneously placed into a level where it is meant to be enjoyed. This is actually what physics is meant to do. We are meant to enjoy physics. It is not meant to be feared. It is usually treated as the most difficult subject. Most people say they hate physics. Most people have one or two bad things to say about physics, but it should be so. Physics is the science of life, the science of the physical world. So if you actually want to understand the physical world, then physics is the way to go. In fact, physics is the base of all sciences, especially engineering. So I want to put you through some examination tips, examination preparation steps. In this course, or in this little discussion, which will focus mainly on solving past questions, we're going to scrutinize so many past questions. And from there, we know the trend which WAEC uses in certain questions. But I want to believe at the end of the day, you're going to, you will believe with me that physics is actually one of the science courses that we got to enjoy. Your examination is starting will take place on the 27th of August. So this series will start from Monday, August the 17th to 22nd. We have a break on Sunday, which is the 23rd, and we go over Monday and Tuesday. So it's going to be an 8-day experience of wonderful physics and stuff. So, like I said again, Professor Quantum. I present to you physics um, at its very, very best. We are going to be using the Zoom platform. So as a matter of fact, I would like you to go through the Zoom app. Just take a few minutes or a few hours just to get yourself acquainted because that is the app we are going to be using to relay this message. And like I also know that so many of you are secondary school students, so I would like you to obtain the permission of your parent. You have to seek the consent of your parent or your guardian, as the case may be. They're going to allow you to come up before you be registered in the group. We're also going to be throwing open a WhatsApp link for those who are interested in joining us. And the WhatsApp link is going to be sent to you shortly. So if you want to belong to the group, you just join the WhatsApp link. And then from there, we'll be communicating as we go on in the lesson. We basically be treating WAEC physics questions. Of course, we're also going to be looking at the JAM, at least to add a little bit of difficulty to it. Because if you are able to solve JAM questions, then I think WAEC will be by the way. So we'll be looking at JAM questions, WAEC questions, and then probably NECO also. So I just want to invite you to this platform. Also on this platform, we will dive into some issues that relate to career progression. Some of us are so confused about what we want to do when we get to the university. We don't actually know what we want to study, especially if you're somebody that loves physics, but you still want some other subjects If still want to join a physics with other subjects. For example, as a medical physicist, I love medicine and I love physics. So it wasn't a coincidence that I landed in medical physics. So if you're somebody who loves physics and you still have an inkling, a kind of love for medicine, I think medical physics is the way to go. So, and so other people, so many other people who might want a kind of direction in the course they want to take in their course of um, in their course in their career progression. On this board, on this group, we also have some other seasoned medical physicists that will be out to actually help us. So let's go. And let's not forget, before each lesson, I would try as much as possible to send to your emails exam questions that you'll be required to answer in a stipulated time. It is meant for us to have the exam feel. When you have a timed exam, a timed quiz, of course, it's going to bring out the review when it comes to exam situation. I'm going to give you, also going to prepare a timed examination question that I'm going to send to you, maybe 40 questions in the 20 minutes. And after the expiration of 20 minutes, you wouldn't see the questions again. So with that in mind, it is meant to prepare us adequately for the exam. And on the WhatsApp group, whatever questions you raise will be as much as possible dealt with. So we are good to go. On this platform, where this is just a demonstration class, on this platform and proper, we are going to always entertain questions. If the class is not too large, because we will have the opportunity of viewing our questions via voice. If not, if the class is too much, we might have to go through the chat channel we have on Zoom. So let's go. I have a question here that I would want us to treat. Some part of the questions. We might not, because of time, we might not get to solve all the questions, but I think we just solve as many questions as possible, because this is a demonstration class. It's just to tell you how the class is going to look like. And again, because of the pandemic with us, COVID-19, it is not possible for so many people to go to people's houses to go and teach them because of safety reasons. So this platform is going to be a block and buster. It's going to become as between one alternative, getting the real classroom experience and also staying safe in your homes. So let's go. So this is the WASSCE exam November, December 2011. Which of the following factors affect the rate of diffusion of a gas? Is the number of atoms, mass of molecule, viscosity, surface tension? We shouldn't have a problem with this. Shouldn't have a problem with this. The relative density of the gas. Okay, sorry, rate of diffusion. Diffusion rate. Actually, must be proportional to mass. And more specifically, the square root of mass, relative molecular mass of the gas. So I don't think we should have should spend time on this question. It's a straightforward question. the rate of diffusion of the gas doesn't depend on the number of atoms, doesn't depend on the viscosity, it doesn't depend on the surface tension, but actually it depends on the mass, the relative molecular mass of the gas. So we shouldn't have any problem with this. And in answering questions, whenever you see a question you shouldn't spend time on, just get going, give the answer and get going, because the time gained in a particular question will definitely be used in some that are a little bit technical or a little bit difficult, especially the ones that come with calculations. This one has got to do with calculations. So we are done. So for the second question, 2 points QR in a room are specified by the coordinates 000 and 111 respectively. Determine the distance Q, the distance QR. I have to share, I have to stop the screen share now and move on. About the first question, sorry, I didn't show you the whiteboard. I didn't highlight the whiteboard. So the rate of diffusion is that is proportional to, it must be proportional to relative molecular mass, which is also the same thing as being proportional to the vapor density. I know the relation that exists between them, between the two relative molecular mass and vapor density of a gas. So that is not our case now. We don't have any problem with this. So we went straight for the mass of the gas. I just had to call this back because it wasn't shown. I didn't highlight the screen then. So we go to the second question. You said a point QR, a question that we just saw. Question, so I should find the distance QR for points Q 0, 0, 0 and point R 1, 1, 1. This is clearly a three-dimensional problem which we have been asked to find the distance QR. I remind us, if we have a two-dimensional problem, it's a two-dimensional Cartesian coordinate, and you have a particular point, maybe P, you could be asked to find the distance from the origin, OP, 0, 0. This is O. So the distance is simply the projection of this on this axis and the projection of this on this axis. So it goes at OP from whatever, from, so this is the right angle. This is right angled here. So OP squared is simply this distance squared. Let's say this is A and this is B. Simply OB squared plus OA squared. As simple as that. So in this particular case, we have been told to find the distance QR. I'm having that as a three-dimensional figure. So a two-dimensional figure for a three-dimensional figure. Let's represent that. As much as possible, when we're solving these objective questions, we might have to go into some theoretical background into the questions. So, because so that I will be using one stone to kill as many birds as possible. So we have that. So for a three-dimensional figure, let me quickly show this. For three-dimensional, we have three mutually perpendicular planes the z plane, the y plane, and the x plane. So if you have a point, any point somewhere, the point you have, assuming you are now asked to find the distance from the origin, say point P. The distance of this object, of this point from the origin, is actually a combination of the distances, a kind of resultant of the distances of this object, the projection of this on this, the projection of this point on this axis, and the projection of this point on this axis. At the end of the day, I don't want to go into the rudiments of how to calculate that, but at the end of the day, because in the first case, you can sum q and x, I mean z and x, to find its distance, to find the distance along the z and x axis. That we use Pythagoras theorem to get a particular value, which on the this zx, the zx axis, you collapse the zx axis. Then the other one will now be for y axis. You could also do for y and z axis, and then find x axis. At the end of the day, you're going to have something like this, which will eventually also give you a right angled whatever, a right angled sorry, a right angled triangle. Right angled triangle at the end of the day. So this will be RP. RP. So what that means that after all said and done, we are going to be left with this QR squared being equal to 1 minus 0 squared, 1 minus 0 squared, plus 1 minus 0 squared, plus 1 minus 0 squared. This actually is a simple equation. So the origin, the point of this Q is on 0, 0, 0, the origin. You could just straight up down the calculation, because this is an objective. We have to gain as much time as possible. You have to gain as much time as possible, but for the benefits of some of us who don't actually know this well, but not for those of you who do further maths. For those of you who offer further maths, this shouldn't be a problem. So we have it as QRs would now be 1 squared plus 1 squared plus 1 squared, which is just 3. 1 plus 1 plus 1 is 1 plus 1 plus 1, which is 3. At the end of the day, we're going to have QR as square root of 3. It's just in its simplest form. You could have combination of points. So for that our question, the answer is root 3. You could have a combination of points, different positions. Okay, you could have, say, minus 1, 3, 2, and R, 3, minus 2, 0. And it has to find the point, I mean the distance QR. It's simple. This is our first point, this is our second point. It doesn't actually matter. This can be our second point, and this can be our first point. It doesn't actually matter. Just that you have to maintain the orientation. If you are taking this to be your first point, every of this value will have to be simultaneous. This is what I mean. If you choose this one to be a second point, our QR will now be QR squared will now be 3 minus 1 squared plus minus 2 minus 3 squared plus 0 minus 2 squared. So if you are taking this to be a second point, to be a second point, you're still going to arrive at the same value of the QR. The modulus of QR in each of the cases will still be the same. So it doesn't matter. So we're going to have 4, 3 plus 1. It's going to be 3 plus 1, 4, 4 squared plus minus 2 minus 3 going to be minus 5 squared, minus 5 squared plus minus 2 squared. So we have 16 plus minus 5 squared is 25. Plus 4. So you see that 20, 20, 25 as 45. We're going to arrive at the same answer. We're going to arrive at the same answer. We have taken this to be a second point. So we move on. So next question. The relative density of ice. Okay. The relative density of ice is 0.9. This statement implies that when a given mass of ice melts, what happens? A very interesting question indeed. We all know that ice floats in water, which is very, very anomalous. As it is not normal. Solids are meant to be denser than liquids, especially if the substances are coming from the same source. What do I mean? Um, if you melt, say, a particular maybe sodium chloride. If you melt sodium chloride in its molten state, it is meant to be less dense than the actual sodium chloride salt. It is meant to be sodium chloride aqueous, not even aqueous, liquid. If you melt this is meant to be. But in the case of water, it is not so. Ice floats in water, and of course, that is why we have life in the ocean during very, very severe cold weather, when it seems that everything in the sea or in the ocean body has actually frozen, but you still have water underneath. So if you have a block of ice floating inside water, have a block of ice floating inside the water. It is going to float with a particular, sorry, I mean, you have a block of ice floating inside water. The block of ice, let me make it bolder. Okay, that should be enough. Okay, I can make it bolder. You have a bucket of water and you've got ice floating. floating inside the water, you're gonna have a portion above the liquid level. You're gonna have a portion inside the water, and also gonna have a portion up in the air. This is as a result of the differences or the difference in density between the water and ice. The level to which the ice sinks into the water tells us the nature of its density. How do I mean? For ice, which is around 0.9 gram per cm cube. As a matter of fact, if you have a relative density of a substance at 0.9 as relative density, what this means is that the density is simply 0.9 gram per cm cube. Relative density is just the comparison of two densities, density of a substance to density of water. For the density of a substance is just added the unit gram per cm cube. That gives you the density of that substance. And we should also know that this is equivalent to 900 kilogram per meter cube. If you do the conversion, I'm going to arrive at that. So for this 0.9 as the relative density of water, it means that when you have ice inside water, you have a block of ice inside water, 0.9 of its volume will be inside the water. 0.9 of its volume will be inside the water, while 0.1 will be outside. That is, its own volume, the volume inside of here will be 0.9, whereas the remaining 0.1 will be outside. If you have a substance whose relative density is 0.5, it means 0.5 will be inside and the 0.5 will be outside. If it is 0.8, it means 0.8 will be inside and the 0.2 will be outside. So that's just the logic there. The more dense a material, the deeper it is going to move inside water. Water is so chosen because the density of the water is 1 gram per cm cube or 1,000 kilogram per meter cube. Being that as it may, it now tells us that from the law of flotation, you know that the body will float when it displaces its own weight in the volume in which it is floating. So for a body to float, it should be able to displace its own weight in the fluid in which it has been immersed in. So if that condition is not met, if you can't meet that condition, then the body can never float. So in this case, for this floating body, 0.9 of its volume will be down there. So what this means is that the weight of the fluid placed, this volume of a 0.9, say, let's give it a numerical value. Let's give it a numerical value. This 0.9, then assume it is 0.9 cm cube. 0.9 cm cube down. Note it. It's this 0.9 cm cube it will displace 0.9 cm cube of water. We're going to displace 0.9 cm cube of water. So at the end of the day, if you now calculate the value of the mass of this 0.9 cm cube of water, it is going to be different from the total mass of this solid, of this ice. But that is not where we are going to. Just for us to understand this, we can now look at the relative density. Let's look at the definition of relative density. Relative density is simply the density of a substance over density of work, which we can move down. We can also have another definition as it is the weight of a substance over weight of equal volume of water. Since weight and mass are directly proportional, weight is actually proportional to mass. We could also use the relation of mass, that is, relative density is mass of a substance over mass of equal volume of water. So, the more the relative density of a substance, the more massive it is, a given of it is. How do I mean? For the ice we have shown 0.9. It means in this 1 cm, a particular, say 1 meter cube or 1 cm cube of ice is about 0.9 times the weight of water. Sorry. Take ice 0.9. It means if you take 1 cm cube of ice, 1 cm cube of ice and 1 cm cube of water, 1 cm cube of ice is going to weigh 0.9 times that of water. For density, for a unit, for say mercury has a relative density 13.6. So it means that 1 cm cube of mercury is going to weigh 13.6 times more than 1 cm cube of water. That is just it. This tells us the mass of a unit volume of a substance, or the weight of a unit volume of a substance with respect to that of water. So, now to our question. So the relative density of ice is 0.9. This statement implies that when a given mass of ice melts, what happens? So let's go there. Let me put that on the board so that I wouldn't. Other question? When a given mass of ice melts, what happens? Let's go back to our whiteboard. When a given mass of ice melts, what happens? I'm going to divide this into two columns. Here, we concentrate on ice, and here we look at water. Let's take ice 0.9, the relative density, which means that the density is cm cube. For water, density of water is 1 gram per cm cube. So when a given mass of ice melts, let's say 0.9 gram of ice, 0.9 gram of ice occupies a volume of 1 cm cube. That's his occupation in terms of volume, 1 cm cube. But for ice, for water, 1 gram of water has a volume of 1 cm cube. That is its own occupation in terms of volume space. So for these, 0.9 gram, this 1 cm cube, this is 1 gram, you're going to give us a 1 cm cube. So let's do the comparison. We either find a 1 gram of this or we find a 0.9 gram of this. Okay, so 0.9 gram of water with what? 1 cm cube times 0.9 gram over 1 gram. So you're going to be left with 0.9 cm cube. So when this mass of this the volume of this, when 0.9 gram of ice melts, which has a volume of 1 cm cube, 0.9 gram of ice, which has a volume of 1 cm cube, when it finishes melting, the volume of water formed would be this 0.9 cm cube. How about that? When 0.9 gram of ice melts, which has a volume of 1 cm cube, the amount of water formed would be 0.9 cm cube. So you see the logic. As ice continues to melt, the volume continues to contract. It continues to reduce in volume. What that means is that the density continues to decrease, because density is actually the relationship between the mass over volume. So if the volume continues to decrease, it means the density is increasing. As the volume decreases, the density is increasing. So at the end of the day, if you have this gram of ice, I mean this mass of ice, 0.9 gram, when it finishes melting, at the end of the day, it's supposed to be 1 cm cube. At the end of the day, when it has melted completely to water, the volume is going to reduce to this value here. So now find the relationship. So the gram, so 1 cm cube of ice over the volume that, I mean 0.9 gram, is going to give us 1 cm cube over that of water. Sorry. The mass of water from, I mean the volume of water from 0.9 cm cube over ice 1 cm cube. I'm going to have this relationship 0.9, which is actually the density. So at the end of the day, the water formed will just be, the volume of water formed is 0.9 times that of ice. It's it looks easy, very very easy. Of course, very very simple. Of course, I'm permitted to use that word simple, just for us to have a full grasp of this knowledge of this topic, relative density. Some tricky questions normally come out from this relative density. So I urge you to just find some time from now till when you write the exam to actually dwell on some of the intricacies that come up with questions on relative density. But this one is a novel example. So with this, I don't think you should have any problem as to um, encountering difficulty when it comes to this subject. So let's go back to that question and see the answers there. Okay. So you can see the volume of water formed will be 0.9 times more than that of ice. The volume of water formed will be 0.9 times that of ice. The two, they look very tricky, but there is nothing tricky there. In fact, as a matter of elimination method, when you see something like this, the volume of water from option B is straight off 0, is just enough. It doesn't make any mathematical sense. The volume of water found will be 0.9 more, 0.9 watt more. You're getting it 0.9 watts more. Is it times more? Or I don't know, it doesn't make any mathematical sense. So V and which one is this? Mass of water form will be 0.9 less, which also doesn't make sense. So V and C actually don't make sense. So you just eliminate them straight off, even if you don't have a full grasp of this particular question. B and D are out of the way. So we are left with A and C. So it's actually the volume of water found will be 0.9 times that of the ice, because the volume of water found will be reduced. So it will be 0.9 times that of the ice. If the question, if the answer here had been, or the option here had been the volume of ice, okay, the volume was to be 0.1, well, it couldn't have come that way. So it is just straight A. So you have to have that. If the question had been the mass of water formed or whatever, it would have been a different case entirely. So instead of comparing the volume at a particular mass we get, we'll be comparing the value of mass a particular volume will yield in terms of water and ice. This is just all that there should be about this question. Well, let's move on to the next one. Question 4. The pressure at the point in a liquid depends on. Okay, pressure and pressure. And we want to go and then look at pressure again. Let me stop the screen. Pressure, okay. Pressure, we all know the definition of pressure as the force over area, force acting a unit area. This is the traditional definition of pressure. But for fluid, we can prove that the pressure in a fluid is actually a rho, density, the h, the height, or the depth at which we want to calculate the depth down in the fluid, the depth down in the liquid, as the case may be. Then G is acceleration due to gravity. Of course, at this, we just have to know that we are immersed in a very, very huge atmospheric pressure. It is the pressure the atmosphere has on us, the pressure the atmosphere confers on us because of the depth to which we are. This is the air. We have the air with an envelope of so many gases and so on and so forth. It's actually these gases that exert this enormous pressure on us, because we are assuming this is the limit from where we are measuring down, say 1 kilometer of air, 1 kilometer of the atmosphere. So if you apply that, we're going to have that unit of rho, the density, the summation of the density, that's the mean density of the atmosphere, of the air, everything there, multiplied by the height from the beginning of the atmosphere down to the surface of the earth. Then acceleration due to gravity, the average acceleration due to gravity. So that's going to give us at the end of the day, 1 atmosphere. It is a 1.0023 whatever times 10 raised to the power 5 and Newton per meter squared. So we have that. We experience this amount of pressure because of the whatever we have in the atmosphere. the various gases we have in the atmosphere. At the end of the day, will exert this enormous amount of pressure on us. So we have that in liquid, the pressure is dependent on the density, the height, and the acceleration due to gravity. It has nothing to do with cross-sectional area. That is, you have a particular vessel, and you have another one, the same height. You have an object here. You have a corresponding object here. You have this liquid. You have this the same liquid. The pressure at this point is simply the difference in this height. So the total pressure this object encounters here is the pressure at the surface, here, and the pressure due to this height. And the pressure due to this height is simply rho hg. So this one, same thing. The pressure at this surface is the same thing with that here. And the pressure at this point, due to this column of liquid, is rho hg. So cross-sectional area has got nothing to do. It has no meaning. It has no effect on the pressure a fluid, an object in a fluid undergoes. Experiences. So as the depth it increases, the pressure differences, or the pressure intensity increases downward. So for mountain climbers, those that go up high mountains, mountain hikers, the pressure they experience up there is very, very low compared to the pressure down here, down on the surface of the earth. Likewise, for those who go down the ocean, who swim down the ocean, ocean divers, experience enormous pressure down below. So that when they come up to the surface of the earth, they have to be placed in a pressure, the contamination vessel, to bring them slowly down to atmospheric pressure, because it just comes straight to the pressure to the outside wall, to the level, sea level. The changes that will occur inside the body might be it might be something the body won't be able to handle. So you've got to be placed in the pressure decontamination bar to slowly bring the pressure down to the level of the one atmosphere, which is the pressure we experience on the surface of the earth. And of course, we know that those mountain climbers, boiling is an issue there. Cooking food properly is an issue because of the low atmospheric pressure. Remember, boiling is when the atmospheric pressure equals the pressure of the boiling liquid. Okay, that's a case for, that's a question that we might encounter some other time. Okay, the question. So the answer is simply 2 and 3. 2 and 3, which is C. 2 and 3. Go to the next question. Which of the following statements about viscosity is correct? Viscosity, I want to believe we all know that. Viscosity is the frictional drag, the frictional force that the fluids experience. That's the drag, the viscous. I don't want to use the word viscous again. The drag experienced by liquids as they move over one another. Okay, let me stop the share and then just do something briefly. You have the pipe. You have liquid flowing through. Now liquid is flowing through. There will be a friction in between this fluid, in between the particle of this fluid, and also friction in between the wall of the container, or the wall of the pipe, and the molecules of the liquid is encountering it at each specific time. We can also explain that you have a liquid container, a drum, you drop something into it, a dense material into it. The rate at which the material goes down the liquid determines how viscous that material is. If the material is very viscous, the object will go down slowly because of the viscous drag that will be experienced between that material, that object, and the molecules of the liquid. Of course, fluid also. Just assume drop a piece of paper in air. That's a viscous and drag. That is why the piece of paper takes some time. It moves in a haphazard manner, but then the direction is downwards because of the air molecule. If there hadn't been any air molecule there, if it's a vacuum, just straight down without any impacts of air molecules or whatever gases. So if you have the rate at which the object goes determines how viscous a liquid is. Okay, let's go back to the question. So which are the following about viscosity is correct? Engine oil is less viscous than water. Is that correct? No, that is not. Viscosity is a property of liquids only. No, it is not. It's a property of fluids, that is liquid and gases. Viscosity increases with rise in temperature. Is that correct? No. For liquid, which is this particular example, viscosity actually decreases with increase in temperature. It increases with, it decreases with increase in temperature. So C is also very wrong. Then we are left with D, which should be the answer, of course, which is illogical. Glycerin is more viscous than water. Yeah. Number 6. The motion of the body is uniform when what happens? That is change in the direction of the body. The speed of the body remains constant. The rate of change of the velocity of the body is constant. Both the speed and direction of the body remain constant. What does that mean? Which shouldn't also be a problem. It's one of the questions in which you spend 1 to 3 seconds and you move on. But the rate of change of the velocity of the body is constant, straight up. And that defines acceleration. Acceleration actually the rate of change of velocity. With time, of course, the rate of change there introduces us to time, the object of time. So the rate of change of the body is constant. So if you have the rate of change of the velocity, the rate of change of velocity being constant, that means acceleration is constant. Hence, we have bodies undergoing uniformly accelerated motion, in which the acceleration is constant. It can be a negative value, it can be a positive value, and it can be zero. When it is a positive, it means the body's speed is increasing. If it is negative, it means it is decelerating, the speed is reducing. And if it is a constant, it means the body is undergoing uniform velocity or the body is at rest. When the body is at rest, the velocity, the acceleration is zero. And when it is moving with uniform velocity, the acceleration is also zero. So these are the cases of uniformly accelerated motion. A, acceleration being positive, acceleration being negative, or acceleration having a null value, 0. So C. So for 7, which of the following distance time graphs drawn above is the motion slowest? I think this should also be a 2-second question. 2 seconds. 3 seconds, maximum 4. How about that? Okay. Let me get that on the board. I'm done in Zoom class. You should be able to juggle between the screen and the video. If you juggle between the screen and the video, there wouldn't be need for me to always stop sharing my screen. You always just press your, just click the video window and we will have it there. But notwithstanding, since this is just meant for demonstration, let me stop the share and look at this graph. We have two bodies, four bodies undergoing different motion. Which is the fastest, which is the slowest? Can we, what do we know about the gradient of, okay, this is distance time graph. Distance time. The slope of this distance time graph is going to give us the speed, distance over time. Change in distance over change in time gives us our speed. So the gradient of this curve is our speed, or the slope. The slope of a distance time graph is essentially the speed of the graph of the body. So we, straight off, the more the slope, the more the value of the slope, the bigger the value of the slope, the bigger the speed of the body. So for this, if you find the slope of this graph, this over this, compare it with the slope of this graph, we find that the slope of this graph will be the highest, will be the biggest of all the four, to have the greatest value of all the four. But that is for purposes of explanation, I wouldn't go that way. I'll look at this graph and draw a line this way. Yes, this one. I want to draw a line perpendicular, parallel to this axis. Draw a line this way. Then I drop down a perpendicular from each point. From here, I drop down this. Here, I drop down this, I drop down this, and I drop down this. Assuming we give this one the value 2 seconds, that's the time in seconds, maybe 2 or 1, 2, maybe 3, or maybe 4. They're not exact, but they are logical. So for this, assuming the speed here is 20, let's say our speed is in meters per second. So it means the speed of this one will be, of this first body, second body, third body, fourth body. The speed of this one will be, of body I, will be 20 over 1, which is 20 meters per second. For 2, the speed will be 20 over 2, which is 10 meters per second. For 3, it will be 20 over 3, which is something meters per second, or 6 point whatever. And for 4, it is 20 over 4, which is 5 meters per second. Straight off, this one has the highest speed, followed by this. So 4 is the one with the slowest speed. It's just as simple as that. 4, the body, 4 is the one with the slowest speed. So as the body, as the slope tilts and towards the vertical, the horizontal axis, the speed continues to reduce. For example, we now have a case where this body lies on this axis. The body lies on this axis. What can we say about that? The special case. In this sense, the body isn't moving. It's a case of a body that is stationary. The speed, the distance covered is zero for as long as the time continues to increase. A body stationary, nothing happens, but time must continue to increase. Time cannot wait. Time waits for no man. Time waits for no event. Time continues to increase. But if you have something of this nature, and the speed is yeah, this one continues to increase so that it hits this, it becomes in parallel to this axis. What happens? That makes no meaning because time must always increase. This one makes no meaning. That's no physical meaning. The body on the distance axis, the distance axis, that doesn't happen. There's nothing like that physically. So 4 is the slowest. 1 is the fastest. Like I said, this is just class that is meant to educate us, that is meant to bring us to some theoretical explanation when it comes, when we have any question, when we come up with any question. So we continue. Well, the area under velocity time graph represents what? The area under a velocity time graph. What does it represent? Before I solve that, before we go to that, again, there are so many questions here that for the snap of your finger, you are done with. This is also an example of that. How? You just give them the answer, just show the answer and move on. Show the answer and move on. So the only time you spend on this question is the time you are going to use in shading your answer. Wow, okay. Okay. Sorry, let me share the screen. Let me stop this screen and move over to the board. Whenever you have any graph whatsoever, and it has to find the area under that graph. The area under that graph simply is the multiplication of the two axes. As simple as that. A multiplication of the two axes. If we have force here, we have time here. The area under a force time graph, a force time graph is simply a force times time. Force times time. That gives us something, what's it called? Momentum or impulse. So the area under a force time graph is simply the impulse of the force. If this is reinforced distance, it is going to be force times distance, FD, which is what? The work done. So the area under a force distance graph is simply the work done by the object. If you have velocity time, the area under a velocity time graph is what? Okay, that was the question. That's the question we're given. Let me use another one, distance. The area under a distance time graph, distance over time, distance multiplied by time. What physical quantity has that? Distance multiplied by time. I'll give you that as a what? As an assignment. Which quantity has its units? Which quantity is the multiplication of the product of force, distance, and time? I give that. Okay. For our case now, we have velocity, we have time. What's the area under a velocity time graph? The unit for velocity is meters per second. The unit for time is second. At times when one has issues with If we are not so sure, we don't have a clear definition of a particular quantity that has got to do with the addition of these two, velocity and time. You might be surprised, velocity and time, what is it? Multiply velocity and time, what do we get? Remember that distance is what? Speed over time. And that might not strike during that particular question. All you need to do is just take the unit of two. You take the unit of the two axes. The unit of velocity is meters per second, meter over second. Multiply by the unit of time, seconds. So you're left with a meter. Which quantity has its unit as meter? Distance, displacement. So the area of the velocity time graph is simply the distance covered, QED, as simple as that. So if you don't know this, the units, the quantity that will be derived from the multiplication of the vertical, the horizontal, whatever. You just look at their units. You go by way of their units and see if you can deduce something there. But this one is a very, very simple one, because at the end of the day, we have a meter as the units that will result from the multiplication of the two axes. So a meter, distance travel. Okay, so we have something else I need to tell us about here. If you have whatever the shape of the graph, of a particular graph, the shape of that particular graph, if the graph is this way, the area of that graph is what? Going to give rise to a triangle. So apply the formula for calculating the area of a triangle. If at the end of the day you have this shape, the area is what? This one here, which is a rectangle. So you simply apply the what? The formula for calculating the area of a triangle. If you are on the end of the day, you have something like this. Simple. You will use this, you calculate the area of the circle, give you the area under this graph. From so many questions we have in the velocity time graph, one of them body increasing in speed, and after I attain the speed, it continues with that speed for some time, and then it's not uniformly decelerated as the case may be. What does this give us? A trapezium. You find the area of this trapezium to give us the area under that graph, which is like the distance covered of velocity time graph. So it depends on the area of the shape of the object. I mean, the shape of the polygon you have here. The shape will determine the value of the area that you are going to use. The figure will determine the area formula you are going to use. So for this question, that's it. That's it. So that's the distance traveled. Area under velocity time graph. The total distance covered. Okay. Let's look at this question 9. Which are the following quantities is a scalar quantity? Which of these quantities is a scalar quantity? Okay. This is also one of the questions that requires us just the time for shading the answer. If it is the CBT computer-based test, it is the time required to just press, to just click the box of the right answer. You will agree with me that physics is something that I don't know. We should be able to come up with a very, very, very good score, because the answer is there. There's no contention about that. It is not some of the languages where you might write something and you have 3 markers, examine your script, and have give you various scores. Though the scores they are almost always very, very similar, as the standard deviation is not so much among the various scores from various examiners. But for physics, you just you have it. If an examiner gives you 10%, I mean 20 over 100, give it to 1 million examiners. They're going to turn the same score. So that is why it is very, very easy to pass all the sciences, physics, chemistry, mathematics, and so on and so forth. Okay, we have that. Which are the following quantities is scalar quantity? We've got magnetic field. Let me put them down. Magnetic field, electric field intensity, electric field intensity, electric potential, electric potential, and magnetic flux density. Okay. Cool. Okay, we'll go back to the board. Excuse me. Yeah. If you can see that properly. The first one is magnetic field, electric field intensity, electric potential, and magnetic flux and density. Magnetic field, just the radial lines that originate from the south pole, from the north pole of the magnet, and then ends in the north pole, in the south pole. The arbitrary lines and so on. These lines these field lines, magnetic field lines, they are directional. So that if you put a small magnet here, you have your north pole here, south pole, you're going to be repelled. Because of the field lines here, that made a kind of a repulsion of the field lines. The repulsion. But if you put a north pole here, there's going to be an attraction. So magnetic field is straight off, it's a density, it's a vector quantity. By extension, magnetic field strength, which is the force per unit and charge. Force per unit charge gives us the magnetic field strength, not magnetic field. It's also a vector quantity. Magnetic field strength gives us the strength of a magnetic field. It's a measure of the strength of a magnetic field. Or electric field intensity. Still the same thing. Electric field intensity is just the electric force over what's it called? The charge. Oh, for this, sorry. This is the charge, Q. So this gives us our magnetic field intensity, which is a vector quantity. It is a very, very serious vector quantity. Electric field at, now the charge, positive charge, electric field is outwards from the positive charge. And if you have a negative charge, you need negative charge, the radially and inside the negative charge. So if you have a small positive body here, small positive charge, placed in the vicinity of this, there's going to be repulsion, and for this attraction. So when you're calculating my electric field strength, one takes cognizance of whether the forces at the end of the day will be attractive or what's it called, repulsive. So if, for example, if you have two charges in which one has a field strength of will be 3 Newton per coulomb. And they have another one towards negative, and they have another one plus 2 Newton per coulomb. We are going to have a summation which is going to give us 3 and 5 Newton per coulomb. Or if it is subtractive, um, we take that, we subtract the smaller value from the bigger value. At the end of the day, the resultant will be the value of the bigger value. Let's say 3 minus 2 as 1. So the sign it's going to have will be dependent on the sign of the bigger value. So electric potential. Electric potential is just the work done in bringing a unit positive charge from infinity to a particular point. You have electric potential, electric field. Okay, you have an electric field. Electric field as a result of a charge, an electric charge. Very, very fine. When you have a body here, you need positive charge. It experiences there is a potential as a result of these two charges. So if you want to, the work done in moving this body, because you are going to be working against gravity, against electric force. So in bringing this body down here, you're going to you should be able to overcome the electric force between these. So the work done in moving this to this is actually a scalar quantity. The work done, this is the energy you use in bringing a unit positive charge. And energy is what? A unit quantity, scalar quantity. Work done is a scalar quantity. So the work done in moving the unit positive charge from infinity to a particular point is a scalar quantity. So that leaves us with the fourth one. You can be lazy and still get this question. You might not know what the magnetic flux density is all about, but you see, I'll be happy because at the end of the day, you still score your point for this particular question without actually knowing it. But we need to know it at this point in time. What is magnetic flux density? Magnetic flux density, given by this sign, is magnetic field strength multiplied by area. I just want to be as basic as possible. Sorry, this is a vector quantity. Area is a scalar quantity. That's a magnetic flux density. Which should this is magnetic flux. If you have been asked about magnetic flux, this should have been a vector quantity. But remember, we are asked of a magnetic field density, which is what? Which is magnetic flux density is simply magnetic flux density is simply base over A, which is P at the end of the day, I have P. So that gives us what? A vector quantity. So this is a vector quantity. Sorry, our answer is electric potential. Sorry. Also fast about that. I'm forgetting the question. The question was actually which of these is a scalar quantity. So this is a scalar quantity. So this is a vector, this is a vector, and this is a vector. So what I wanted to say then was that without knowing this, since we have gotten to know that this is a scalar quantity, just go for this without actually knowing what without knowing what magnetic flux density should be or is. So even without knowing what magnetic flux density, you are so comfortable after arriving at this being your answer. So electric potential is the only a scalar quantity we have there. Every other thing is a vector quantity. Mind you, magnetic flux is a vector quantity. Magnetic flux density is a vector quantity. So we have this also is a vector quantity. Magnetic flux density is also a vector quantity. magnetic flux is also a vector quantity because this vector multiplied by the scalar doesn't change. Doesn't change it. It still remains a vector. Okay. Um. Okay. I thought I wasn't. I was using the screen. Two forces of magnitude 30 at right angle to each other. It's another question that requires question. Very, very simple. Oh my God. Okay. This makes our physics look very, very inviting. It's all these questions. Okay. Two forces. 30 meters. 40 meters. Resultant. Whenever I see these numbers 30, 40, to find their resultant, because you know that resultant will be the third Pythagorean triple. You know, 3, 4, 5. 3, 4, 5 is a Pythagorean triple. So 5 is one. They are potentials. So with this, just 30, 40, and 50. Multiply 10 to 10. That's all. Move on. So 50 is what? A resultant. Are we good to go? Okay. For some of us that might need a little explanation on this is what we need. We have two forces inclined at an angle of 30 degrees, 90 degrees. So I find the resultant. The resultant is simply you complete this parallelogram, which is a square. And the resultant is this angle, the diagonal drawn from a common point. So you can see resultant is coming from here to here, or move here and then move there. So R is a resultant. At the end of the day, we're going to have what? R squared is what? 30 squared plus 14 squared. Remember, this is a right angle triangle. So that's why we're using the Pythagoras theorem. We're going to have 900 plus 1,600, which is 2,500. R is square root of 2,500, which is 50. Square root of 2,500, that's 50. So we'll move on. 50 Newton. Remember, this is subjective. We don't have any issue with doing the things in terms of a unit. And when we get to a theory, then we've got to apply all we know when it comes to the appropriate unit for all questions. Okay. It's also a bonus question. Let's go to another. 11. The energy in light, in a light beam travels through space in concentrated packets called straight off. It's not food, it's not electron, it's not proton, it's not neutron, it's not neutron, it's not proton, it's not electron. Photons. 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 You hadn't seen photon there. If you had seen something like quanta, you would have gone for quanta also. Either photons or quanta. So they travel in a concentrated packet called a photon. Uniform half-meter rule, AB, balanced horizontally on the knife edge. Knife edge A, B, half meter rule, half meter rule. Oh, the distance, 20 centimeter. So the distance this is 20 centimeter. This is 0. This is a 50. And have an object on point A on A. Diameter of knife edge with a mass of 1300 A. This means mass A is 30 gram. Okay, let's go back to our board. So we have that. So how do we do it? How do we do about it? What's the mass of the meter rule? The meter rule, this is uniform. The mass should be here, should be acting downwards. Acting, the center of gravity should be acting downwards at the center of gravity of the meter rule. At 25. So we have that. What is it? What time is this for? Pakistan. Okay. We have this from a principle of moments. The clockwise moment should be equal to the anti-clockwise moment. So about this fulcrum, this body will tend to tilt this way. This body and this fulcrum, because of this weight, the body will tend to undergo anti-clockwise rotation this way. Whereas the mass of the rule, we tend to make this body undergo clockwise direction. So our principle of moment says that the anti-clockwise moment should be equal to the clockwise moment for a body in rotational equilibrium, one of the laws of equilibrium. So we have this moment of this about this point is simply this weight multiplied by this. The weight of this body is what we can do with mass. We can do with mass because mass is directly proportional to weight. Instead of converting this into weight, converting to Newton, to kilogram, then from kilogram you move to weight, you convert this, and at the end of the day, you find the weight of this one, which is going to be Newton. Then you now convert, you move back to mass in kilogram, then mass in gram. We don't have that luxury of time. So we have to state it. If this were to be a theoretical in theory, it's a part of the question. You've got to say that since weight is directly proportional to mass. So we can say in place of weight, we will use mass. And that's enough. That's enough for you. That saves you the stress of doing all those conversion. Because if you're actually doing the principle of moment, moment is what? The force multiplied by the perpendicular distance. So if you state this, you've been covered. So we go straight and then use the masses in something in going about our problem. So 30 multiplied by this distance, which is centimeters, which is also okay. We don't need to convert to meters. 0 times 30 times 20 equals the mass of this meter rule n multiplied by the distance from here, 25 minus 25. And then they have mass to be 30 times 20 over 5 or 120. So the mass of the meter rule is 120 grams. This is also one of the questions that you don't need to spend so much time. The time you just need is to just put your diagram down. For questions like this, you need to put the diagrams down. If you can't juggle with those figures in your brain, but if you can do that without any mistakes, just go up and then spend them as little time as possible, especially for those of us who will be writing jam. Can we handle more questions? Okay, let's see. Okay, I love this. The body executing simple harmonic motion has an angular speed of angular speed of 2 radians per second and maximum displacement of 5 centimeters. What determine the magnitude of its acceleration? So, determine the magnitude of its acceleration. Before I go on this question, I'd like to do some theoretical background. We know that angular speed is theta over time. Yeah, theta is the angle a body undergoing, which is the same thing for circular motion. Because when the body is rotating this way, undergoing circular motion this way. At some point it is here, at some point it is here, an angle theta in time t. Angular velocity is simply theta over the time it has taken to move from this angle, from this position to here. By the end of the day, the displacement is x. Displacement is x. Here the amplitude, the maximum displacement is a. The radius of that circle. You can actually represent this. This is a representation of simple harmonic motion using graph. Using circular motion. I explain simple harmonic motion using circular motion. When the body starts from rest, from here, it is here. After a particular time, theta, the body is somewhere here. At 90 degrees, 5 over 2 radian, the body is here, 90 degrees, which is here. That gives us a maximum displacement, 90 degrees. After some time, after 200 and 180 degrees, displacement is now 0 again. You can see this displacement is now 0. At this point, the displacement is here. Only from here to here. But at 180 degrees, displacement is now 0. Continue to grow, displacement continues to increase until it gets to maximum again the other way, which is here, 270 degrees. Then at 360 degrees, it comes back here. So we can use this to explain simple harmonic motion. So having done this, we go to say using cosine that our x is a cos theta. Cos theta is what? Adjacent over hypotenuse. So therefore, the adjacent side due to this angle is a cos theta. Also, we have been sharing this screen. Oh my God. I've been sharing this screen instead of. I'm sorry about that. I have to go over this again. Sorry about that. Oh, so. You can actually see what I went through, but it wouldn't be enlarged. I said, a body undergoing simple harmonic motion can be represented with a circular motion. But starting from here, after some time, gets here, theta, it travels angle theta in particular time. This is the maximum displacement. after something, this is the displacement, whereas this is the maximum displacement. The maximum displacement is the area, is the radius of that circle. So the angular displacement, angular velocity is theta over time. I said we can represent this. This is circular motion which can be used to describe simple harmonic motion. And when the body starts here, it is here. When it gets to this angle theta, maybe around here, this is our x. As it continues to move, our x turns to r here. I mean a here at 90 degrees, which is here. When it gets here, x becomes a. Continues again, goes here. Our x now turns to a value here, maybe x2, so on and so forth. It continues until it gets here again, where our x now turns to a again, which is the maximum here. A. It continues down here. Sorry, this is 180. When it gets here, x becomes 0. It lies on this axis. It continues till 270 degrees this way, where you now have minus a, another maximum in the other direction. Then continues till one gets here, 0. So we have actually succeeded in plotting this graph on the circular, on this circle. So having done that, we can move on to say that x is a cos theta, because on x, cos theta is what? Adjacent of the hypotenuse. The adjacent of this, the adjacent due to this angle over the hypotenuse. And if at a, cos theta is what? Omega t. And theta is omega t. So a cos omega t. If you differentiate this with respect to time, the x over the t, is going to give us velocity. And velocity is simply what? If you differentiate this one with respect to t, you're going to have minus omega a sine omega t. Differentiation. We should know a bit of this, even though of course, this is physics. We should have a very, at least a knowledge, some good knowledge of differentiation and some integrations. Not too required, but we need to do that. So that's for velocity. If you further differentiate this with respect to t again, the squared x over the t squared will give us acceleration, which is, say this, the minus omega squared a cos omega t. That's acceleration. The question demands wanted us to get the acceleration. So that's our acceleration, a cos omega t. But we know that a cos omega t is what? A cos omega t is our x. So instead of that, we just see a is what? Minus omega squared x. At any point in time, this is the acceleration. The acceleration will be maximum at this point. Positive maximum here, and the negative maximum at this point. At this point, acceleration is 0. At this point, acceleration is 0. So we are good to go. So for that question, we're going to use this. I need to use this. So let's go. Let's share the screen again. So that leaves us with so the speed is 2 radians per second, 2 radians per second, and then The displacement is 5 centimeters. 5 centimeters. Let me go back to the board again and complete. So have the speed, the angular speed as 2 radians per second. So you're going to have omega squared as 2 times 2 multiplied by the displacement, which is 5 meters. 5 centimeters at 0.5 meters. So we are left with 4 times 5, 20 over 100, which is 0.2. So 0.2 meters per second squared is our acceleration. So 0.2 meters per second squared is the acceleration of the body, and the maximum acceleration. The acceleration continues changing at every point in time. So let's see, you can go to 14 and we probably wrap it up until we come again, we come live on Monday. Let me put the values down on the board. First, 20 kilogram, 20 kilogram, 20 to 30 meters per second. Okay. Just simply go straight. Second law of motion that F is what? Rate of change of momentum time V minus U all over T. And from our second law, using some second law of motion, if you have our Ft is mv minus U. So this is also a straightforward question. You might need to spend a little time. Because for some of us who do mental calculation, all you need to do is 10 minus this, 30 minus 20, 10 multiplied by 20, 200. As you go, you move on. So Ft is actually the impulse of a force, which is the same thing as the rate of change of a momentum. The impulse of a force is the same thing as the rate of change of momentum. That is why you have the impulse of a force, Newton second, being equivalent to kilogram meters per second, unit of momentum. You can see that at the end of the day, if you do the dimensional analysis of these two units, you will find out that they are essentially the same thing. We have the impulse of the force is what? M, which is the mass 20, final velocity, which is 30, the body move from 20 to 30 minus initial. So 20 times 10 gives us 200 Newton second. Newton second. And the impulse of the force. So the change in momentum of that force is 200 kilogram per meter, 200 kilograms per meter. Was positive. If the body had reduced the velocity from 30 to 20, the value here would have been negative. I want to call it a day with this question, just for us to know that I feel this is something that we should love to do, not just because of examination sake, but because of the love we have for physics. If that is your approach, then I believe you will be turning out good grades when it comes to physics and just with every other subject you love. So I want to encourage you to develop this special love for physics, and I bet you're going to be good for it. So thank you very much. Until next time, which we meet, which will be on Monday. I'm going to send a message across, which will bear a link to the WhatsApp group, which is going to be used for this purpose, for disseminating information. Like I said again, just feel free, just go through the Zoom app, because that is what we are going to be using for this program, for this 8-day intensive lecture. The lecture, or rather, the exam preparation for physics is going to come up from say three to around 5. We are going to be flexible around this area. So on a particular day, I will have your thoughts on the best time for this preparation for this time. Usually in the evening, maybe from 3 to 5 or thereabout 5:30 at the case may be. You can make it 4 to 6 at the case may be, 5 to 7, depending on your choice. So we always discuss that every day on the group so that we carry everybody along. Because I believe that some of you will be involved in one exam or the other, which might make one of these times not to be favorable. So I join you to join, tell your parents about that, and have their consent. So until Monday, until we see on our WhatsApp group, which I will send across, is a goodbye from Professor Quantum.